All right, we're being recorded now, starting on our Monday, April 13th class. Maybe I'll start out with a question. I noticed that about half of us have our video playing and half of us don't. Personally, as the person running this session, it is way easier for me to read if people are following along by seeing everyone's faces, but some people might not be comfortable with that. So if you are comfortable showing your image, I much prefer that because I get to see you all, feels a little more personal. You can see each other's faces and been like, why is everyone else confused? And I can speak up. It also allows me to read the room, and a whole bunch of blank screens make that more difficult. So if you're comfortable and have a video camera, please show your video. Don't have to, but that's just a personal request for me. Do we have any logistical questions for today? Concept logistic questions. Okay. Once again, don't forget, I am available on office hours for the 2 hours leading up to class at 3 to 5 p.m. on Mondays, and whenever else you guys need. So just go ahead and shoot me an email and I'll make myself available. And I'll stay after class as well. So before or after class, you can always ask me a question. All right. Today, we are going to spend a bit more time kind of bringing the connections together from lab and class. And so I'm going to share with you the screen. So I've already sent a clicker question out. Clicker question is up and running. So this relates really specifically to what y'all have done in lab. So we're talking about adding hydroxide from sodium hydroxide, potassium hydroxide, calcium hydroxide, doesn't matter what the source is. But we're taking that hydroxide and we're adding it to HCl. So the question is, if 1 mole of hydroxide is going to interact with, consume no protons, some, a full mole or 2 moles. Go ahead and click in your response. And we're going to split out to groups for the next couple of questions. And this one just really sets the stage for what we're doing today. Looks like we guys want to make it in. All right, 15 responses. I think we have more than that. Has everyone clicked in their response? Okay. So we have a majority of our class answering this question with our answer is C. And so I guess I can show that now. So majority of people are saying C. So hopefully from titrations lab, you've seen a couple of different times now, if you add a strong base like hydroxide, then that reacts in a 1-to-1 molar fashion, and you end up consuming a 1 mole of protons. We're going to start talking about whether that needs to be a full, a strong mole, a strong proton, or a weak proton, and we're also going to talk about that, what it means in terms of bases the other way around as well. But the basic equation that we're talking about here is acid-base chemistry means that a proton is transferred from one object or one molecule to another molecule, and the simplified kind of distilled down version is H plus OH minus leads to H2O. So let's do our next question. And then for this next question, I want you thinking about this in terms of limiting reagent, just like you've done in your titration lab. So limiting reagents was something we did in first semester Gen Chem, but the concepts are very much utilized here. It's really just stoichiometry, saying if we know the ratio of how many react, which one runs out first. Okay, so we're gonna go ahead and ask the next question. And I'm gonna send you into breakout rooms for this question, so we'll be back in a minute. I'm going to send you into breakout rooms, and then I'm going to start the return for 1 minute, so you guys can choose how quickly you want to come back. I'm just gonna make sure that we have these rooms evenly divided. Okay. Some of you are not yet assigned. All right, everyone should be assigned. All right, has everyone got a chance to get assigned? All right, looks like there's one person on the phone. Can you hear me? Hello, hello? Sam. Can you hear me? Hello?
Hi, Dr. Bailey. I wasn't sent into a group. I think that's what's happening right now.
So I just closed out the groups, but it looks like you were sent to a group. It just didn't link you out there.
Okay.
So can you see the question though that we're working on?
Mm-hmm.
Okay. So Aislinn, were you able to hear when you called in as well as the video? Thumbs up, thumbs down. You can also try leaving the Zoom message room and coming back in. That might allow you to connect with audio through your computer. All right. So we got 19 responses. Let's take a look. Looks like we're kind of distributed between B and C for the most part. So can I hear someone? Can we have Samuel? What did your group talk about with this question, and how did you answer it?
We actually didn't talk about much, but I wasn't sure. I originally chose A, but I wasn't sure if that was right. And so I switched back to C because I knew that the base would like absorb or whatever a hydrogen atom, or a proton. I just wasn't sure how many it would like take.
Okay. Taylor Arnold, it looks like maybe you're chewing. Do you have a second to give your additional input in between bites? I appreciate you showing your face.
My thought process was, since it's a weak acid, it won't dissociate completely. So I said it would consume some, but not a full mole of proton.
Okay, fantastic. So if that acid goes into water, it's a weak acid by definition. It doesn't release a full proton. So which one is it? Does anyone have a really strong opinion? They want to like, it absolutely is this one?
No, not really.
Who was that? I heard a voice for a second there.
Alex.
Hey, Alex. So what did you think and why on this question? Have you been able to follow along? I saw you've been kind of popped in and out of the session.
Yes, I agree with Taylor. I did say it was going to consume some, but I wasn't sure if it was just 1 mole or if it was C or B.
Okay, so we're basically split between C or B. And here's the thing that's hopefully going to be super duper clear. Strong acid or strong base. If those are ever present in an acid-base reaction, they will always react until completely gone. So if you have a weak base with a weak acid, yeah, then it's true that you're going to have a little bit reacting with a little bit because they're weak. But if either one of them is strong, it's going to go until you are completely done. So anytime you have a strong base reacting with any type of acid, it is a limiting reagent problem. So as you can see here, that doesn't matter if this acid is weak or strong. If this is strong, it's going to go until there is no hydroxide left. That is always going to be completely used up. So then let's take a look at the next question. So our next question is, if we're adding a strong acid, HNO3 or something like that, that completely dissociates, right, our definition of a strong acid, and we add that to a solution of a weak base, we have two of them shown at the top of the image. I'm sharing my screen, right? Yes. Okay. Just wanted to make sure that I hadn't stopped doing that and I was just talking to myself. So weak base pyridine is the one with the nitrogen of the lone pair in the ring. And then we have carbonic acid is the second one. Well, bicarbonate because it has one proton. So these are both two bases. So I'm going to send you into breakout rooms again, and I want you, under the framework we just discussed, to talk about how to answer this question. I am going to do this one for just 1 minute though. So as soon as I send you there, I'm going to hit the close rooms, so you'll have 60 seconds to come back. Go. Michael, you already kicked back out? Did you mean to do that?
No, I didn't.
Can I send you back into the room, or can you jump? I think you can select to go back if you wanted to. The bottom of your screen, is there an option to go back?
There's leave meeting. I think that
But
might
there's
be-
no option for join group?
No.
Well, shoot. Okay, you want to tell me what you're thinking on this one?
I guess maybe A, if it would protonate anywhere until it was completely.
So you think that it doesn't matter whether it's an OH minus or strong or weak base is what you're saying?
I think so.
We got a lot of people coming back. The clock timeout. Is everyone back now? All right, looks like we got everybody back. I'm going to take a look at the results. If you haven't clicked in, looks like we don't have all of our responses in yet. So go ahead and submit your response. And I think it's safe to say that our answers are all over the place. Does that sound about right? So maybe the wording is not as clear as I would have liked. Is that part of it? Okay, so clear wording. So the first answer is that H plus is going to protonate, which means be attached to any site that has a basic property, whether that's a weak base or a strong base. The second one says, nope, that H plus will only react if there's an OH minus. And that third one is that one proton can go to multiple different sites and protonate more than one site. With that new explanation, go ahead and select your answer. Change if you would like. It looks like we went from 40, 40, 20 to all over the place. Interesting. Okay. So can I hear from someone who kind of had a discussion or thinks that they might have an idea of how this would work? I'll ask for a volunteer here. Bueller.
I think it's going to give a proton to just about anything that'll take it.
So which answer would that be?
I think A.
All right. That would be A, and I agree. All right, so this idea that a strong acid or strong base is always going to be the limiting reagent, and it will always be used up completely, is something we want to keep in mind. That's the definition of a titration. A titration is that you know that whatever you're adding is going to always be completely used up. And that whenever if you keep adding something, so let's say you have an acid in solution, doesn't matter if it's strong or weak, if you keep adding OH minus to that, whenever you add some OH minus, you're going to take away a little bit of whatever the acid is. You add more OH minus, takes away a little bit more, little bit more, little bit more. Then all of a sudden, when you add some more base past the equivalence point, then all of a sudden your pH becomes really basic. So the definition of titration is whatever you're adding has to be a reactant that always gets completely used up. And so the two examples here, nitric acid plus pyridine is completely used up, that this is always a complete reaction. And here is the one with the bicarbonate. And you'll notice that both of these are full-headed arrows, just like dissolving of a salt or dissociation of a strong acid or a strong base. These reactions always go to completion. If you have any of this left over afterwards, then you have an equilibrium reaction. But if you have a strong acid or strong base, they will always go to completion, regardless of the strong or weakness of the other reactant in the reaction. Okay. So this is always the limiting reagent problem, meaning we're always going to use up one in the stoichiometric ratio. You notice that almost all of our acid-base reactions have a 1-to-1 stoichiometry, but that's not always the case. So keep that in mind when we go further. So today I want you to be able to tell me how to make a buffer. That's going to be a really important component of what we're talking about today. I want you to be able to calculate the pH of a buffer solution, which you've already done, but we're going to do some more. And we're going to do that before we add anything to the solution. And then we're going to try to calculate the pH after we've added either strong acid or strong base. And then in the big picture, I want you to talk about how it is that a buffer minimizes changes to pH. So to start with, I'm going to ask you to come up with a definition in your group of what a buffer is. And sometimes that might help to describe that in terms of what does it mean outside of chemistry, and then what does it mean in chemistry? Okay, so there's two things. What does a buffer mean outside of chemistry, and what does it mean in chemistry? So I'm going to send us to our breakout rooms, and I want you to take about 2 minutes to come up with a nice definition, and don't just Google it. It's not about that. I want you to think about what a buffer means, all right? So I'm going to go ahead and open the rooms, and I'll give you 2 minutes. Are you three able to join a room? Gabby, it looks like I have assigned you to a room. There should be a little pop-up saying join breakout room 2. Can you see it? Aislinn, are you able to hear and see? Yes, no. All right. Looks like we got almost everybody back. So can I have, let's have Sydney McCann. What did your group decide was a real world example of buffering?
We didn't really give an example of like a real world one. We just kind of had to ponder back and forth what a buffer was. It took us a while.
Okay, so you want to talk about the chemistry version or non-chemistry version?
I guess just the definition.
Okay, what did you come up with?
We just said that it was like resists change by neutralizing something. It either protonates or absorbs.
So you were saying it protonates or
Absorbs.
okay. I'm not quite sure what the absorbs part means, but maybe we'll kind of flesh that out as we keep talking through this. Lauren, were you in a different group than Sydney?
We were in the same group.
Okay. Did you want to add anything to that or?
She pretty much covered everything we said. Yeah, it just kind of helps to maintain the pH.
Okay. Samantha, were you in a different group?
I can see what
yes.
I got Patrick muted. What did your group talk about with what is buffering and ideally some non-chemistry examples?
We didn't really talk about non-chemistry examples either.
Okay, do you have anything to add to this definition?
No.
All right, can I hear from someone in another group that might have discussed non-chemistry applications?
Our group said something that's used to prevent or stop change.
Okay, and I sat in on Patrick's group, and one of the discussions they had was your computer or your TV will say buffering. And it talks about, I'm sure that everyone's able to join here. It looks like someone is. So if we're talking about buffering in your download capability, it means that something is not functioning properly. It means it's slowing down a process. In families, a lot of times people talk about someone's a buffer between you and your, let's say I really don't get along well with my brother. I'll say my mom is a buffer between me and my brother. And so that buffer means that it takes a harsh change and it softens it. It kind of like smooths it out. It makes it less aggressive of something. And so in chemistry, this idea here that we've been talking about with resisting change, it's not that it maintains the pH. I would actually change that terminology. And I would say it minimizes the magnitude. That's a nod. Of change. So it takes something that would have been a really big change and it makes it a smaller change. It still changes. We can't stop it from changing. That's not what a buffer does. A lot of people have the misconception that a buffer stops all change and it just makes things stable, and that is not the case. So we're going to talk about exactly how that happens. But before we do that, I'm going to continue on one more component here. And it looks like someone got kicked out. Let's get back in. The other question I have is if we have a solution of a weak base like ammonia, I think this is one of the questions on your worksheet, how would we make a buffer solution out of that? So one of the things we didn't talk about, we said what a buffer does, but we didn't really talk about what a buffer is. So this will kind of help us down that line. So do you want to do breakout rooms for 1 minute? Thumbs up, thumbs down, breakout room. All right, breakout room for 1 minute if I can get it to pop up. Breakout room. All right, 1 minute. what is a buffer made of and how does it relate to this question? That's what I want you to talk about. All right, that was a bit of an abrupt ending to the group meetings, but hopefully you're able to get some conversation done. So can I ask Danielle to share what your group was talking about?
So my group was talking about how you would have to have an acid and its conjugate pair or a base and its conjugate pair. But like for this one, since it's a base, we would need its conjugate acid.
Okay, so we'd have to have a conjugate acid of ammonia. Great, so the thing we didn't talk about during that last question was a buffer is made of an acid and a base. Does it have to be a conjugate acid base pair? Thumbs up for yes, thumbs down for no. I see 70% thumbs up, so I'm going to say yes. So it has to be conjugate pair of an acid and base. You can have multiple conjugate pairs, but that's a more complex buffer. So the minimum requirements for a buffer is at least one conjugate acid base pair. And then there's a qualifier on that. What's a qualifier on that acid base pair, conjugate pair? Does it have to be strong? Does it have to be weak? Do both have to be weak? Do both have to be strong?
It's a 10-to-1 ratio.
Okay, so the amount of them can at most be 10-to-1. You can also have 1-to-1. You can have 1-to-10 ratio. Those are all fine. Once you have more than 10 times as much of one than the other, it's no longer a buffer. But what about the strength of the weak versus strong? Any thoughts on that? Can both of them be strong? Can one of them be strong? Can we make a buffer from HCl and Cl minus? That's a conjugate acid base pair, right? Thumbs up for yeah, that's a buffer. Thumbs down for no, that's not a buffer. Yes, it's a buffer. HCl, no, it's not a buffer. I only see a few thumbs. Can we give me thumbs up for yes, HCl and Cl minus are a buffer? Okay, absolutely not. So HCl is a strong acid. That means it is only going to dissociate into Cl minus. That base, so our Ka is so high, right? The Ka for that is 100 or 1,000. That means our Kb for Cl minus is like 1 × 10⁻17th. That's like such a weak base, we don't even count it as a base. So in order to have a conjugate acid base pair, both of them have to be weak. I don't know if you can see my hands. I don't know how I'm showing up on your screens, but I'm trying to show the relative Ka and Kb values. Because remember, Ka times Kb is always the same number. So the bigger one is, the smaller the other is. So if you have a strong acid, it means that that conjugate base is so low that it's not even a base at all. So Cl minus is not a base, so it cannot act in the capacity that we need to in a buffer. Amber?
You're not sharing your screen.
I know. Oh,
Okay.
I'm also trying to share my screen. I was trying to do both. You're right. Let me share. Can you see my screen now? But now I can't see you guys. Let me see if I can get out of this. I can move back to here. And then let's see if I can redo. All right. I believe. Can I get a thumbs up now, Amber? Can you see my screen with the writing on it? Okay, thanks. So HCl and Cl minus are not a conjugate acid base pair that can make a buffer. They are a conjugate acid base pair, but they don't have enough basic strength in order to be a buffer. So Cl minus, not a base. So the closer together your conjugate acid base pair are, the more you consider both of them weak. So a typical acetic acid, right, has a Ka of 10 to the negative 4th or 10 to the negative 5th Ka. That means the Kb is 10 to the negative 8th. Those are both considered weak. So you have to have a weak. One of the things I've heard in the side discussions that comes up frequently is that your homework says, well, you have to have, the stronger the acid is, the weaker its conjugate base is. That's true, but once you get outside of both of them being weak, then you no longer have the other one is considered a base. So HCl is an acid, strong acid, Cl minus is not considered a base. I feel like I'm repeating myself a bit here. So there's two ways that we could make the conjugate acid base pair. So we said that it has to be a weak acid base conjugate pair, and it can be a weak base acid conjugate pair. It doesn't matter which one it is, as long as both are weak. This one is a weak base. You'd have to have its conjugate acid. So we would have NH3 is ammonia, and we'd have to have NH4 plus. That pairing would make it into a buffer. If we had both of those, and as Tracy pointed out, we have to have a substantial amount of both. It has to be at least a 10-to-1 ratio, if not closer. If we have a 1-to-1 ratio, that's an ideal kind of typical buffer mixture, is to have the same concentration of both. So then how do we make it? How do we make a solution if we have only ammonia to start with? How do we make a solution that has ammonium or NH4 plus in it? Anyone discuss that in their groups? Can I hear from Taylor? Can I hear from Taylor in the green shirt? I'm sorry, I can't remember your last name off the top of my head. Not Taylor Arnold.
Me, Taylor Gamble. Okay. I really don't know. Would you add more NH4?
How do you add NH4? Where does that, how do we get NH4? Because it doesn't exist by itself. We can't just grab a bottle of an ion.
Oh. Okay. Then would you add a different base so that those, or acid, so that those that a H proton can then be transferred to an NH3 to make NH4?
Exactly. So if we have NH3 and we add H plus from some source, a strong acid, then these two are going to combine until the strong acid is totally used up. And that means that if we have, let's say we had 100 of these to start with and we added 10 H pluses, then in the end, we're going to have 90 of the NH3s. We're going to use all of this up, and we're going to then make 10 of the NH4 pluses. So now we have a 9-to-1 ratio of a weak base and its conjugate acid. The other way we could do it is although NH4 plus doesn't exist in a bottle, NH4Cl is a salt that does exist in a bottle. And we can shake some of that into solution, add that with our ammonia, NH3, and that's another way we can make a buffer. So there's two different ways you can make a buffer. So let's take a look at once we have a buffer and then we add a strong acid or a strong base to that. I'm going to let's think about the concept of this first. So when we add a strong acid, which is it going to have a stronger effect on the pH of? A beaker of water, a beaker of a buffer, or both will have the same change in pH? Sixteen responses. All right, a couple more seconds. All right. So we're kind of split between two of the answers. Kevin, can I hear what you answered and why?
Well, I thought of it like from the primer when we did a simulation. I said B because when we added a buffer, kind of like changed. I think the pH went up when we added the buffer.
So just a little clarification there. Usually when you have a buffer, that's the thing that things are added to. So that's the receiving solution. So what we add to the buffer is going to be a strong acid or a strong base. And so the question is, if we're doing that, does adding the strong, in this case, strong acid, does that have a bigger impact on pH on a buffer or on a plain water solution? And so it looks like the majority of the class agreed with you in that you're going to have a smaller change in pH when you add a strong acid to water. And I want you to think about why. How does the buffer do what we just talked about? We just said that a buffer minimizes change in pH. It doesn't stop it from changing, but it minimizes it. Is this worth doing a little group discussion on? Thumbs up if this is worth group, or we don't think we need to. All right, I see a lot of thumbs down. Is that because we know what we're talking about, or it might not be a very productive discussion? Let's go ahead and look at, I'm gonna have you write down your answer to this as we go through the next couple slides, okay? So I want you to write down how it is that a buffer minimizes the change in pH. Okay. So in doing that, there's two things I want you to think about. I want you to think about, if we have a buffer, list two things that happen when you add a strong base that releases hydroxide, OH minus. And I want you to list two things that happen when you add a strong acid that generates H plus in solution, okay? So those are the two framing questions that's on your worksheet for tonight. So I want you to try to fill in at least two things specifically that happen that help minimize the change in pH. Okay, here's my visual. This is kind of a ghetto visual. But the point of this visual is to say that each one of these blocks represents the quantity of our weak acid conjugate base pair. The bigger the box is, the higher the concentration or the number of moles in the solution. I know that they don't exist separate by themselves like this, right? They're mixed together and they're floating all about, but I'm trying to show how much we have of our weak acid conjugate base pair. Right now, how would we say that we know the pH of the solution is? Based on the concentration of these two, what can you say about the pH of the solution? Super vague and generic.
It's neutral.
Okay, where are you getting that from?
There are equal concentrations of the acid and its conjugate base.
Fantastic. I completely agree, but I disagree with your conclusion that it's neutral. Can someone else help tweak that a little bit? What is it we know when we have the same concentration of a conjugate acid and its base?
It's at equilibrium.
So all of these would be at equilibrium. It's just
So it's going to be
Would it be
less than 7, right?
Yeah, because it has the H3O too in excess.
Oh yeah, that makes sense.
Well, so it's showing that there's some H3O plus that's released. There's also some OH minuses there. I didn't show that. I probably should have. But what is always true when you have the same concentration of a conjugate acid base pair? What is the pH in a solution where we have an equal concentration of conjugate acid base pair?
Is it because of the arrows? If it completely disassociates or not?
Well, we have some on both sides of the arrow, and so it's kind of reached equilibrium. But remember the Henderson-Hasselbalch equation? What happens to the
Would
Henderson?
it be?
Say again, Stacy?
Would it be equal to the pKa or close to it?
It would be exactly equal to pKa if we have an equal concentration of a conjugate acid, conjugate base pair. Okay, so we're starting out with a solution that's pH equals pKa. And to that solution, I'm going to say that we are adding a strong base hydroxide to that solution. What's going to happen to the hydroxide that we add to solution? Based on the discussion that we've just had up until this point, what happens to the OH minus when we add that to solution?
The acid component will neutralize it, or?
So the OH minus reacts with our weak acid. With the size here representing the number of them, which one is going to run out first? The OH minus or the HAs? The weak acid.
The OH minus.
So we have less of the OH minus, and it's a 1-to-1 stoichiometry because each OH minus reacts with one H plus that's pulled off of a weak acid. So my little cheesy animation here shows, that was terrible timed. It shows the OH minus reacting with the HA. Every single OH minus that reacts with an HA forms water, which I'm not showing because it's everywhere here, plus it releases an A minus. Every single OH minus creates one conjugate base. And then if we want to show that as an equilibrium, what's on which side, right? We can say that we took some of the weak acid, converted it to the conjugate base. So if we go back to those questions I just asked, what happens when we add OH minus to a buffer mixture? Can anyone answer at least two things that we know happen when you add OH minus to a buffer? Can I hear from Nick? What happens when you add OH minus to a mixture of a weak acid and its conjugate base?
Will it just not like change, I guess, or not a lot?
Well, so let's be more specific. What actually happens to that OH minus? What are the steps that we just kind of saw?
Oh, are we just saying that it like this, that it completely dissociates?
Right. So if we added NaOH, we would say it completely disassociates and releases an OH minus. But then what happens to this OH minus when it is in solution? What are the steps that we just kind of went through?
I'm kind of getting confused, honestly, on the process.
Tracy, can I ask you to help out?
Yeah, it takes a proton from the acid and makes H2O, and then it becomes another conjugate. A conjugate base is also created.
So big picture, what Tracy said is that each hydroxide will react with one acidic proton in that HA. And then when it does that, each OH minus is essentially converted into a weak base. So when we're talking about a buffer, what has a bigger impact on pH of a solution? If we add hydroxide by itself, or if we add the same amount of a weak base? What's gonna have a bigger impact on the pH? OH minus or A minus? Sorry, neighbor's dogs are right outside the window. I don't know how to mute my screen. So what do you think about that? The original, if we go back, if we're thinking here, right? We're saying, is it gonna be OH minus in solution? If we just had water and we added OH minus, then we have that much OH minus in solution. But if we're adding OH minus to the buffer, we end up converting that OH minus through the interaction with the weak acid to the exact same amount. So it's either A minus is being added to solution, or if there wasn't a buffer, it would just be OH minus. Front row.
Okay, so the OH is a strong base, so that's why the pH doesn't change, because it changes it to a weak base?
Exactly.
Okay.
So buffers work by converting a strong something into a weak something. The problem with a buffer ends up being, if we had this much OH minus, then we would be able to use up all of our buffering capacity. If we don't have enough, if the limiting reagent is the weak that it's reacting with, then it's no longer a good buffer, because then we can't convert the strong at base to a weak base. So let's take a look at another example. So we're going to look at, we just showed a buffer, pH equals pKa, becoming more basic by interacting with OH minus. The next one, we still have initial starting pH equals pKa. And then in this case, we're going to add H3O plus. So I want to have you think about what's going to happen to that H3O plus, and then how's that going to impact the pH as compared to if we were adding H3O plus just into water. So can I hear from Verda? What do you think is going to happen to that H3O plus that's added to water, and how's that going to impact the pH of the solution, the buffer?
So it would react with the A minus, right?
Okay, can you get a little bit closer to your microphone? I think I agree with what you're saying, but it's a little hard to hear you.
Can you hear me better? This is about as close as I can get.
Yep, sounds good.
Okay, I said it would react with the A minus, right? And then it would subsequently form more HA.
Absolutely.
Then that HA, right.
So then, using the terminology that Tracy used about weak and strong, how does a buffer minimize the change in pH when a strong acid is added? Verda, you can go ahead and answer that, or we can pass the baton if you want.
We can pass it.
I remember she said it changes it into a weak base. If it's a strong acid, it will be changed to the conjugate weak base, I think.
So what Tracy was talking about is when a strong base is added, it's converted into a weak base by interacting with the buffer. In this case, we're adding a strong acid. So what happens to that strong acid when it's put into a buffer solution?
Becomes
so I think we might have had a little bit of buffering issue with the audio connection there. But if we kind of look back at how we were discussing this before, that our strong acid was basically converted into a weak acid that still makes it more acidic, but to a lesser extent. So if we're talking about our steps, strong acid reacts with a weak base. Strong acid is converted into a weak acid. pH change is minimized compared to if you added just a strong acid to water, because a strong acid became a weak acid. Once again, if we had had more, if we go back one more step here, if we had had more H3O plus than we did the A minus, which we don't in this case, I showed the amount by the size, then we would have used up our buffering capacity and we no longer would have had a buffered reaction. We would have had a very acidic solution if the H3O plus was actually bigger than the amount of A minus that we had. How digi am I getting? It looks like my screen's freezing every once in a while. Are you guys seeing a lot of diginess on my end? A little bit. Okay, we'll try to keep going. All right, so let's take that. And I want to ask a question here. So we're gonna have to go back and use our stoichiometric mindsets. I'm gonna throw you into breakout groups for a couple of minutes here, and I want you to answer this question here. If I can get my breakout rooms to show up.
I guess we're the first one done. And during the last breakout session, when I was explaining the 10-to-1 ratio, I was trying to explain it for when you have a weak base and if you add a strong acid. I don't know if I was clear about that.
Sorry, say that again.
You know, during our last breakout session, when I said that you would have, yeah, I was just trying to explain that you would have to have a 10-to-1 ratio for when you have to make a buffer for strong acid and weak base, or weak acid or strong base.
Okay, thank you.
Amber, you have a pigeon in your room? What is going on? Amber, what bird is that? Amber, what's going on?
What?
You had a bird flying around in your room. What do you mean, what?
Yeah, that's one of my birds. I mean,
Oh, it's like, no. Okay.
that's one of my. I have 3 pet pigeons. So.
What? Said no one ever?
That's okay, Amber. I got a pet squirrel.
Nice.
Bizarre. All right, we've got almost everyone back. I think one more or 2 more. And it looks like everyone is clicking in with the same answer. So how do we go about answering this? Can I hear from Sydney Chastain? How did your group answer this question?
So what we did is we took since it was already in milliliters, we didn't feel like we needed to convert it. So we put 50 times the molar of 2.0, and then we divided that by 1,000 to get 0.1. And then we did the same method for the other one, so 0.4 times 250 milliliters divided by 1,000, and we also got 0.1.
Okay, so I'm gonna tease this apart a little bit more. Looks like I froze my screen with y'all on it. So that big M, I always want us, like I said earlier in the semester, to unpack that. So if you have the big M, remember big M is hiding the units of moles per 1 liter of solution. So if you're saying we have 50 milliliters of a 2 molar solution, this is how we write it out. It's 50 milliliters times 2 moles per of acetic acid per 1 liter of solution. And so that tells us that we have 100 millimoles of acetic acid. If you notice, I didn't cancel out the M, I canceled out the liters, but I left the milli. And so that milli goes in front of the moles. So we can have 100 millimoles. And then I think Sydney said we did the same thing for 250 milliliters of our solution of sodium acetate. And we have 0.40 moles of CH3, CO2, and A per 1 liter. And then one step that maybe not everyone put in there was that for every 1 mole of sodium acetate, it releases 1 mole of acetate ions in solution. Okay. That end result is that we have a solution, conjugate acid base pair, where we have the same number of moles of each, which is why I think everyone selected pH equals pKa. So in order to do those calculations though, Sydney, your group must have gone through a couple discussions first, right? How did you decide that you just needed to find the number of moles of your conjugate acid base pair?
We didn't go into a big depth about that. We just knew that we needed to compare the two of them, and you had mentioned stoichiometry, so we figured that was the best route to go.
Sorry, I lost you at the end there. Your audio is going in and out a little bit. I'm not sure if the phone's a little bit away from you or computer.
We didn't discuss like exactly what we needed to do, but we knew that we needed to compare the two, and you had mentioned that we needed to use stoichiometry.
Okay, so can I have someone describe why we compare these two? Specifically, what about this? What about these two things makes you want to compare them? Let's just try to be really explicit.
Is it because they're a conjugate acid base pair?
Great. So the first thing we need to do is we need to think, do we have a neutralization reaction? Is there a strong something reacting with the opposite? Strong acid reacting with some base, strong base reacting with some acid. If so, then we need to say, well, which one is there more of, and then figure out the pH. In this case, we say, well, there's a conjugate acid base pair. The only difference is the Na versus the H. So that's an acidic proton, CO2H, and the other one doesn't have it. All right. And then once we do that, we say, okay, well, I know I can find the pH if I know how many moles of each there are. So Henderson-Hasselbalch, right, says pH equals pKa plus log of the conjugate base over acid. All right. So we're on the same page for how to go through that. So we start with a solution of pH equals pKa. Then the question is, what happens to the pH after we've added 1 milliliter to 1 milliliter of calcium hydroxide, that's 1.5 molar in concentration, to this solution. So go ahead and I'm going to close that first one out. We were all on the same page. I'm going to go ahead and open the second question. After we add calcium hydroxide, what's going to happen to the pH? Is it going to be greater, equal to, or less than pKa? And I'll give you 30 seconds to answer this, and then we're going to calculate it. Couple more seconds. So this is the mixture we just had, pH equals pKa. We're adding calcium hydroxide to it. And Aislinn, what did you say happens to the pH of the solution after you add calcium hydroxide?
I don't know. I just kind of picked one.
Okay. Tina, what are your thoughts and why?
Okay.
I was thinking about C.
So what is calcium hydroxide? What is it we're adding to this buffer?
A strong base.
Absolutely. So if we add a strong base to any solution, what's going to happen to the pH?
It will increase.
It's going to go up. Absolutely agree. So pH of the solution is going to go up because we're adding a strong base to a solution. Because it's added to a buffer, it means it's not going to go up as much as if it was added to pure water. So at the molecular level, remember, we're taking a strong base. It's going to use up some of the weak acid and make a conjugate base of that. I want you to calculate what that pH is going to be after that change has occurred. So I did a little bit of the calculations here for you. And let's see, it's frozen. Okay, so I want, if you notice, I took the concentrations in the last question and I converted it into moles of everything. So I have the moles of your acetic acid, moles of your acetate, the total volume that that solution was, that was pH equals pKa. And then to that solution, I'm saying that we're adding 1.5 millimoles or 0.00150 moles of calcium hydroxide. I want you to try for about 2 minutes to think about how we would solve for the pH of the solution. This is very similar to what you've done in lab. And then after 2 minutes in groups, I'm going to have us discuss this and kind of talk through it as class. Tracy, you able to jump out to a group? Don't you always feel like class isn't long enough? Or is that just me?
It's pretty short.
We're trying to have people work through it instead of you just see me work through it. It feels like class is always too short. All right, we're getting at the end of class here. So big picture, I hope that what your facilitators were able to push you towards is this idea that if we're adding a strong base, it's going to react with the weak acid. And so we have a mixture, a conjugate acid base pair. I'm gonna skip through this. We have our calcium hydroxide. Remember, every one calcium hydroxide releases 2 hydroxides. So that means our solution not only has a mixture of a weak acid, its conjugate base, hydroxide, and then 2 spectator ions. So what we're really interested in is how is that neutralization reaction going to proceed? Every one acetic acid is going to consume 1 hydroxide. When it does that, that's going to produce 1 acetate. So we're basically using up our weak acid to make some more of that weak base. So here's a tool that I typically use myself when I do these calculations. I say, it's called an ICF table, not to be confused with an ICE table. An ICE table is about an equilibrium reaction. This is not. This is a limiting reagent tool that we use to talk about how much do we start with and what's used up. So it's about limiting reagents. So this particular reaction, we have 0.100 moles of each of our conjugate acid base pair, and we have 0.00150 moles of our hydroxide. We really don't care about, well, we do care. I'm just going to skip that statement. We're going to use up our weak acid until either all the weak acid or all the hydroxides used up. Did I mess anything up here before I go any further? Or what did I mess up? I already messed something up. What should be different in my table?
There's 2 OHs for every calcium hydroxide, so then that means you have to double the moles amount of it.
Great, so 0.00150 moles of calcium hydroxide actually makes 0.00300 moles of hydroxide. And then when these are consumed, the weak acid, the acetic acid, they make the conjugate base. So that means I'm converting some of the weak acid into its conjugate base. And I'm going to use up all of my strong base. That means that in the end, this is all gone. We used up some of our weak acid, and we converted that to our conjugate base. So once again, we minimize the impact of the hydroxide and the change in pH by converting it into A- by reacting it with the weak acid and the conjugate acid base pair. So how do I find the pH of the solution? The last step. I'm going to wait for someone to answer this. Anyone want to unmute and answer?
Would you use the Hasselbalch?
How would I do that?
That's a good question.
What was this, 4.754? Was that the pKa of acetic acid? Something about that. Plus log of, now here's a small trick that you can use. We're going to put the moles of our base, 0.103, over the total volume of the solution, which was 301 milliliters, is that right? Over our moles of our acid over 301 milliliters. And what you're going to see is that every time we use a Henderson-Hasselbalch equation, the solution, it's the same solution. So we can actually just use, for this part over here, we can instead write log of the moles of the ratio is the only thing that matters for that fraction at the end. So if we do this, we're going to calculate the pH is higher than pKa. And so what do we end up finding? 1.8 10 to the negative fifth negative log 4.74. So this is actually 7.745 is the pKa. We're going to do plus log of 103 over 97. So I end up getting that the pH equals 4.77. 1 if we want to add another digit. Okay. We are way over time. You can tell Hemendra it's totally my fault. I'm sure he'll be okay with that. I apologize for anyone else that has things they're going to right now. But take home message is that if we're working on an acid-base mixture, if we add a strong acid or a strong base to that solution, it's going to use up whatever the opposite of that strong is until we have none of it left. In class on Wednesday, we're going to talk about how a titration curve relates to what we just talked about and what the pH of those solutions are after the fact. All right. I hope you have a good night. I'm going to stop sharing my screen, and you're welcome to stick around if you want to discuss any of what we talked about tonight, or if you have any questions.